So far, we studied 4 different types of varying annuities. That's sections from 1 to 4. In this video, we are going to learn a new type, that is continuously payable varying annuities. As the section title says, in this particular video, we're going to focus on continuously payable annuities. Usually, this type of annuities is a little challenging. That's because some of you may have hard time imagining how payments can be made continuously. Usually, that is a challenging part. To me, the best way to understand the continuous payment is from a calculus point of view, right? So when you have a function like this, how do you calculate the area enclosed or below this curve? This is a straight line. So if I want to know the area, let's say between A and B, I need to do integral, right? Let's call this function f. So if I want to know the area, this shaded area, I will need to integrate from A to B of this function, right? Let's call this x axis. Continuously payable annuities is similar to this before we assume the rate is a constant. So in our previous studies, so this is your payment rate. So let's assume this is $1, okay? That means not dollar. Dollar is not the amount, so let me erase this. So it should be $1 per year. So what it means, this is a rate function. This is not a payment function, okay? So in order to know the amount you will be received, then you need to multiply by how many years. So if you need 1 year, okay, then this area gives you the amount that is $1, right? So that's why when you have continuously payable annuities, you need axis. You need x-axis, like a timeline. So this should be time. So previously, like for a standard annuity, a fixed payment is made at a single point. Now payments are made continuously from the starting time to the end time. So it's continuously instead of a single dot. Right? Single dots refers to annuity immediate, annuity due, those standard annuities. If you have continuously payable annuities, you have a continuous function. So anytime when you want to know the amount you need an interval from time horizon to do the shaded area. Of course, here it's more complicated because we don't just want this area. That's not what we need, because we either want to know the present value or the future value. And the payments at different times, they're going to have to be discounted differently, right? So this point is closer to 0, so it will be discounted less. This point is a little further away from 0, so it will be discounted more. So you need to also times by a discounting factor. So that's why, previously what we have is, let's say you want from 0 to n, right? So at any point t, this is your discounting factor, right? V to the t's power times by the payment rate is 1, and a short period is dt. So that's why I believe in chapter 2, this is the formula, or this is the result we need to derive the present value of a standard continuously payable annuity. Here, it is not standard because the amount is not flat. The amount over any fixed period is no longer flat. The rate function will be some strange curve or may grow like this or may decreasing like this. Previously, we have a flat line. Okay, so that's something we're going to study in today's video. So let's take a look at the default setup. What is the definition? Here we have $1 continuously payable in the first year. So which means over the first year, if you ignore the discounting factor for a moment, the total amount will be $1. In the next year or in the second year, the total amount received will be $2. So if you use rate, this will be 1 per year. Here it will be 2 per year. Right? That means, roughly speaking, you will have this kind of shape. So again, this is the rate function, the payment rate function. In order to convert it into the amount of payment, you need some time. Okay, you need a time interval to convert the rate to amount. Obviously, what we are interested in is still the present value and then the future value. Once you know the present value, the future value, it's very easy. You just need to multiply by this accumulated value factor. Since this is for n years, so this is the n year accumulated value factor. First, we have this result. This is not surprising at all, right? So if you recall, what is the standard increasing annuity immediate for n years at interest rate I? This is annuity due minus n times v to the nth divided by I. Okay? So what is the difference? It's here. Right? This remains the same when we study the level annuities. Right? If your annuity immediate, the denominator is I. If you study annuity due, the denominator is D. If you study continuously payable, then the denominator is delta. So here, it's the same logic. By the way, you should know the relation between I and delta. Right? So this is the equality between 1 year effective interest rate and the force of interest. From here, you can actually get delta is actually smaller than the 1 year effective. This is not surprising because we are trying to equate them, and force of interest, this is the limit case of compounding. You have infinite many numbers of compounding over each year. Okay, let's take a look at how we can derive this, how we can understand this formula. Okay, so basically, if you look at the definition, if you only look at for 1 year, if you look at the first year, it is let me get to the next page to we have some space. If you only look at first year, it is continuously payable with rate 1, right? So that is right. This is for the first year. Right, this is a trivial example, right, from what we already studied in chapter 2. Next, I consider for the second year. In the second year, the payment rate is no longer 1, but 2, right? $2 per year. But it is still a continuously payable annuity. Again, the term is only for 1 year because I only look at the second year. But however, if I want to know the present value, I will need to times by a discounting factor because I only look at the second year, right? So it's this. So when I look at the second year, okay, my present value inside the bracket is at time 1. In order to go to time 0, I need to times by 1 year discounting factor. This is for the second year. Okay, so etc. You should easily follow what you need to do. In the last one, it is still a continuously payable annuity for 1 year because we decompose everything year by year, right? So this is for the last year, the nth year. And then you need to figure out what would be the discounting factor. So let me extend this line. So the last payment is over this year, right? Continuously from n-1 to n. So this point is the starting point of the nth year. This is where I get my present value. So in order to go from point n-1 to 0, I will need to multiply by this discounting factor, right? So from here, I can easily factor out this 1 year present value, and then what's left inside will be 1 plus 2v. Then here is obviously 3v squared, goes all the way to nv, right? So the inside part should look somehow familiar to you because that is increasing annuity due for n years, right? The first payment is at time 0, so it's $1. There's no need to do any discounting. The second payment is $2, which is paid at the beginning of year 2, that is the end of year 1. So you need to discount by 1 year factor, so etc. Right? So this we know, right, which is the annuity due for n years minus n times Vn divided by d, right? Because this is annuity due, so we divided by d. Okay, so the next question is, what is this guy? Right, this is just 1 year. So let me cross it out and then replace it. So let's cross this out and then replace by, right? It's 1 year, so I don't need to, well, if you want, you can put 1 here. And I divide by delta because this is continuously payable, right? So 1 minus v is exactly d, so this will cancel. So this goes back to the formula in the previous page. So if you want to go, here is exactly what I have done here, right? So I just derived this formula to help you understand. But of course, in order to derive this result, I did use something from the previous result. Okay. Next, once we started the immediate case, okay, by the way, there's no need to discuss between continuously payable, immediate, or continuously payable due because there is no such concept. Right? If your payments are made at discrete times, it is important to talk about whether it's made at the beginning or at the end. But now we have a continuous, right? So it's continuously paid from 0 to 1. Right? There's no beginning, there's no end. At any instant second, you will get something. So there's no need to distinguish. That's why I put it here. But of course, there are many more things we can discuss. Right? So here we have n payments, n years, not exactly n payments. Right? We go from year 1 to year n. What if n goes to infinity? Then it is a perpetuity. Right? So we have continuously payable increasing perpetuity. For perpetuity, in the notation, you change from n to infinity. Right? So that's what we are trying to do. Right? We actually take limit for n to infinity. Right? If this is the case, we know this will go to 0. Right? And your annuity due becomes the perpetuity due, and this is 1 over d. Right? So that's why we have this formula. Right? So once we know the standard result, we simply take the limit of n to infinity. Then you easily derive the present value for continuously payable increasing perpetuity. Right? So the name is a little bit wrong. So here continuously is reflected in here. right? So this means it's continuously payable. Increasing is reflected by this capital letter I. Perpetuity is reflected by this infinity sign. Okay, so that basically explains everything in this long name. The opposite side obviously is the decreasing annuity, right? So we have standard decreasing, we have decreasing perpetuity. Again, everything is the same to what we already studied. Technically speaking, you just replace the denominator from I. So there are three choices, right? If it's immediate, you divide it by I. If it's a due, you divide it by D. If it is continuous payable, you divide it by delta. So technically, if you really want to memorize the formula, please memorize for the immediate case. Right? Then everything else, it's just the denominator is different. Everything else is actually the same. Let's look at the example 3.7. If you have textbook, that's page 72. So let's study example 3.7. Determine the present value of payments of $50 continuously in year 1, 60 in year 2, 70 in year 3, and so on up to $140 continuously in year 10. Annual effective interest rate is 6%. We want to know the present value. Okay. This obviously is not the default setup, right? It's not 1, 2, 3 all the way, right? You start with 50, and the next one is not a multiplier of 50. So you need to, when you have this, the first thing you do is to figure out what is the increment, right? In the standard setup, it's 1. In the default case, right? It is 1, 2, 3, 4 all the way to n. Obviously, between any two numbers, the increment is 1. Right now, it's 50, 60, 70, 80, all the way to 140. So the change is $10 between any two consecutive years. Okay? So once you know that, what are you going to do? You break or you decompose the payments, right? So the first one is 50. Well, you leave this, right? The second one is 60. So this is year 1. This is year 2. This is year 10. Right? The reason for this decomposition is almost obvious by this moment, right? Because all the 40s we can take care of it, right? Which is 40. So remember, this is continuously payable. So I'm going to put a bar on top of 8. So it's 8 bar angle 10 at 6%. This is level. This is a level annuity, right? The payment rate is $40 each year. Okay, so it's a level continuously payable annuity for 10 years. But the bottom one is not. Right? So it's 10, 20, well, so which means I should factor out this one. Right? Then it's an increasing continuously payable annuity, right? And it is also for 10 years. The interest rate is also 6%, right? And then you can you apply whatever the formula you have. Okay, it's basically here we have two formulas, right? One for the so one for the standard case, right? This is level. This is increasing. If you want, you can apply formulas to calculate this result. What's next one? Next is 3.8. 3.8 determines the present value of a series of payments of $100 continuously in year 1, $90 continuously in year 2, goes on to down to $10 continuously in year 10. Well, this is a standard decreasing annuity, right? And it's continuously payable. So I put a bar on top of A for 10 years, right? So you can directly apply the formula. So please do carry out to finish those two examples, right? You need to practice on those, right? Otherwise, when you do the exam, you almost think you know how to solve, but in the end you get something wrong, then you are going to lose all the points. Right? So practice a little bit more, right? So here we have two examples. You can change this to anything, right? So here you start with $50. You can start with any amount, right? So I can start with $200. Okay, it continuously payable in year one. Then I can go to, let's say I can go to 240, right? And then I should go to 280, etc. Right? You can end at any number you want. And the same reason, if you want to try to apply the decreasing continuously payable annuity, you can start with any number. You don't have to start with 100, right? You can try a different one. Okay, you can also start with 200, and then I go down to 195, and then I go down to 190. I don't need to end at year 10. I can add at year 20 if I want, right? So try different numbers, try different years, try different interest rates, right? Get some practice. Here, the good thing of this course is you can make up any number, and then that will help you test whether you understand, right? Because sometimes if you do the same thing as textbook, you feel you can handle, but if the numbers are different, if the setup is different, you may have trouble. That's why I'm actually asking you to make up any numbers to try on your own. Okay, I will stop here for this section, and we'll continue on the next part. Is slightly more complicated, but we can handle, I'm sure, about of that.